The handout today is substitution reactions. Ready to start substitution and elimination reactions. SN1, SN2, E1, E2. Substitution and elimination reactions. Two different types of reactions. With alkenes, we covered addition reactions. Addition reactions of alkenes, very important. Substitution reactions, elimination reactions, also very important. What do these reactions have in common? Substitution, elimination. These occur in a tetrahedral carbon, not an alkene carbon, tetrahedral carbon, sp3. These reactions will also have what we call a leaving group. We will get to that. This is a substitution handout. There will also be an elimination handout. Let's look at mass spec, the one where we were assigning structures to mass spec. This here. Let me also first pass back the lab from yesterday. I didn't get it passed back. This is just from yesterday's group. If you please yell when I call your name. If not, you can pick it up in office hours. Let's do this quickly. Abdul? Here. Crystal? Here. Trey? Here. Name on the back, please. I reckon this was a little bit different than the report. Abdul, Crystal, Connor, here. Abraham, here. Andy, Mai, here. Asia, here. Sarah, here. Valerie, here. Minna, here. Camille? Here. Precious? John? Here. AJ? James? Joy? Today in lab we will be meeting downstairs. You got my email yesterday. 2:30. Okay, let's look at these. Three mass specs, three compounds. First thing I would do is look at the compound and say, what do we predict? We predict alpha cleavage as the main cleavage. Alpha cleavage basically means we're going to cleave to leave a cation next to what? Long pair or a pi bond. This molecule here we can cleave here to give that radical plus that cation. Cation next to a lone pair. We could show resonance there. But in terms of what this would be M minus, what did we lose? That's a propyl, that's M minus 43 equals what? What's the molecular weight of this molecule? 1, 2, 3, 4, 5, C5, 8 something O. It's all saturated, so this should be what? 12. 5 times 12 is 60, 72, 16, 88. M minus 43, 88 minus 43 is what? 45? Yes. So we expect to peak at 45 for that compound. We can also cleave where? Here? No. That would put cation where? On oxygen? That's not next to a lone pair. That's on an atom with a lone pair. No. What can we cleave over here? Yeah, just an H. I mean, this is a CH2H, right? It's a methyl. We can cleave the H, and we could get boop, 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 OCH2 plus H radical. That cation resonance stabilized. This would be M minus 1 equals what, 87? So, alpha cleavage would give 87 and 45 for the first one. What would it give for the second one? Well, we can cleave here. This would give that cation next to a lone pair plus CH3 radical. That would be M minus 15. That's 15 equals 88 minus 15 is what, 73? That's different from over there. We could also cleave here to get just an ethyl radical plus that cation next to a lone pair. This would be M minus 29. 88 minus 29 is 59. So for the second one, we expect 73 and 59. We could also expect loss of an H here to give 87. I'm not going to do that one. This compound, alpha cleavage here to give cation there next to a lone pair would be O-methyl plus there next to the lone pair plus CH3 radical. That's M minus 15. M minus 15 is 73. Cleave methyl is all 73. Or we can cleave H. But I don't see a 59 here. And up there was totally different. That was 87 and 45. Well, let's look at what we have. The first mass spec, some things were labeled. Molecular ion of 88 is here. Base peak of 73, loss of 15. Which one did we predict 73? The second and the third. But the second we also predicted 59. Do we also have a 59? No. Only 73, no 59, so that doesn't support that one. Only 73. This is compound 1, 2, and 3. So is this compound 3? Let's tentatively say that's 3. Compound 3, the third one. Let's look at the next mass spectrum. Here we have a 73 and a 59. Did we predict 73 and 59? That was the second compound. I mean, that one didn't even have a 59. We predicted 59 for the second one, so this is the second one tentatively. Let's see if the third one has 8745. That's 45, check. Does it have 87? This is not really labeled and there's no tick marks. That's probably 88. It definitely has 45. We predicted 45 for the first one. We did not predict a 45 for the second or third. It looks like the third mass spec is the first compound. So it was, in terms of mass specs, it was 321. Do we want to stick with 321 or do we see a need to reconsider? Did anybody get anything else? Satisfied with 321? Was there a peak that we didn't identify? This one up here had 73, predicted 73. What is this 57? Somebody labeled it here, and then I wrote something. What is 57 for compound 3? Well, 57 would be M minus what?
31.
M minus 31? How could this lose 31?
Include the oxygen.
Well, actually, probably right here, because that could be a tertiary cation. Cleave that to give. That's not alpha cleavage. We're not putting cation next to a lone pair, but we are making a very stable tertiary cation. Plus O-methyl radical. This should be 4 times 12, 48, 9 H's. This should be 57. Indeed, that's another way that we could say, yes, the first spectrum does look like compound 3 because we also have a 57. More support for that being compound 3. Questions about those? This afternoon we'll work some from the workbook. That's what we did yesterday. Ones in the workbook are very similar. There's a couple in there that have IRs, and for example, no structures at all. We'll work that one of those this afternoon. That's mass spec. There's a couple of miscellaneous things on the front. They're using mass spec to detect cancer. Sort of direct analysis. On the very back, it talks about direct analysis of pills. Usually you have to do, when you do mass spec, you do it in solution. You guys yesterday did mass spec, you dissolved it in the solvent, your sample. Yeah, and then you injected it with a syringe. On the back, they're showing how you just hold a pill up to the inlet port, and it just pulls molecules off the pill. You know, it's getting easier and easier. On the back, anybody want to get a job one day? John? No? Asian? Job? They're looking for a mass spectrometrist at GlaxoSmithKline. Drug companies really value people who can analyze compounds. That's a pretty old job ad, but there's one like that every month in like CNN News magazine. Well, that's mass spec. Experience, able to run mass specs, able to identify peak compounds using mass spec.
So did they do what we did yesterday, all day, every day?
Yeah, but they have problems. I mean, they have, you know, new drug syntheses.
They have to figure out what the solvent
What solvent is best for running mass spec? There's different types of techniques. Not all compounds can be analyzed by electron impact, because electron impact ionization will destroy some molecules. So there's new techniques that have been developed or that may be under research to be developed. Figuring out what technique is best for ionization. The GC component has lots of variability. What type of column is used for the GC? What type of conditions are used? What type of pressure? What type of heat? You know, when you went up there yesterday, everything was kind of ready to go. Okay. Nucleophilic substitution at a tetraneutral carbon. Here's a synthesis of Allegra. Anybody taking Allegra this week? Yeah? Here's the molecule right here. Here's a synthesis of it. And right here is a substitution reaction. We're going to call them SN1 or SN2. Substitution reaction. Replacing something. It's like a replacement reaction. Not an addition, but a replacement or substitution. This is done, well, let's go ahead and look at it. You can look back at that once we kind of introduce some stuff. Here's a general line reaction here. We're going to have two reactants. Electrophile, nucleophile. We're going to have some type of carbon with a leaving group. That's what this is. X is a leaving group, or I call it Lg. The leaving group is eventually going to leave the molecule. It's going to be replaced and substituted off. The leaving group is on what type of carbon? Tetrahedral, and no other type. If it's on a trigonal-planar carbon, you cannot do this chemistry. Okay? We do the substitution at a tetrahedral carbon. The leaving group is replaced by generally what we call a nucleophile. What is a nucleophile like? The nucleus. What's the charge of a nucleus? So this thing likes positive. So what's going to be the charge of the nucleophile? Negative. Now it may be an anion, negative, but it doesn't have to be negative. It could be neutral, but it's going to have a lone pair. And we know lone pairs are negative, but maybe not a formal negative charge. It's going to have a lone pair. And this thing is going to replace the X group. The X group has left the building. It served as a leaving group. The nucleophile replaced it or substituted it off. It's a substitution reaction, not an addition. Your best leaving groups are typically halogens, with the larger halogens being better. Iodine better than bromine, bromine better than chlorine, and that's much better than fluorine. Other types of atoms can be leaving groups though. Here's a precise example of the generic example. Maybe the leaving group is bromine on a tetrahedral carbon. Maybe the nucleophile is hydroxide. Actually an anion here. This would like a positive. Call that a nucleophile. The hydroxide has replaced the bromine. The bromine left. The bromine was the leaving group. Substitution. So, what's the mechanism for this? I'm going to show two possible mechanisms. We're going to call them SN1 or SN2. I'm going to show two mechanisms, and then we're going to say, okay, which one is most likely the mechanism? Why is it the mechanism, and why is the other one not the mechanism? Now, the one that is not the mechanism here, we will use that mechanism later. Both of these will be used, but only one applies to this example reaction. So let's look at it. How can we replace the Br with this? Get this. Does everybody agree that Br has to leave? Well, one thing we could show is we could just show it leaving. That is, these electrons just break away, move on to the bromine. What would that arrow movement give? This is just a Br leaving. Can a Br just leave an atom? Yeah, we've shown this before. What happens if you put HBr in water? It ionizes. The Br just leaves, and when it leaves, what do you get? H plus. There's three lone pairs there. What does this mean? The bonding pair is moving on to the bromine as a fourth lone pair. Ionization. This is facilitated by a polar solvent. Bromine can leave an H. Can bromine leave a carbon? Yes, it can. We can show that here. If bromine left, what would we get? What would this carbon become? Positive, and we would make what? Br minus. We got to make that. Right there, we just made that. That's a possible way to make Br minus. That's a possible way for the Br to leave, which it leaves. What do you want to call that? Same thing we called it over here. What do you want to call this step? Ionization. We make two ions. So we could propose that the first step is ionization. Leaving group leaving. How could we then get the final product, this product? What would we need to do? These electrons, remember when we do arrows, we start by saying what? These electrons add to the plus and make a covalent bond. What would that give? That would give the product. Oxygen now bonded. One of the lone pairs is now a bonding pair. Two lone pairs left. So I just showed a possible two-step mechanism. Ionization, the leaving group leaving, followed by the nucleophile attacking the carbocation. What do you want to call this other than nucleophile attacking carbocation? That's pretty much it. I'm going to call this nucleophilic, don't let this term confuse you, addition. Isn't this adding to this? Overall, the reaction is not an addition. Overall, the reaction is what?
Substitution.
Yes. But we can call this second step nucleophilic addition to the carbocation. Okay, what do you think about that mechanism? You like it? You see any problems with it? Can you assess it? Y'all know Bloom's taxonomy? Levels of learning? Isn't assessment one of those levels? Yeah? I think so. Can you assess this? How do you like it? Any problems with it? You like it? You love it? You hate it? Anybody hate something about it? What type of carbocation did we make? You like primary carbocations? No. This is primary. Primary carbocation is usually bad. Bad, very bad. Usually. Usually want to avoid primary carbocations. Still a plausible mechanism. Let's do a reaction coordinate diagram for this mechanism. Reaction progress. Some type of energy here. We started out with alkyl bromide. That is an alkyl bromide, right? We ended up with an alcohol. It's hard to say which is more stable because it's the same number of bonds. We didn't like make sigma bonds or pi bonds. I'm just going to put this at the same position. That's not really that critical. Did we have any intermediate?
Negative primary.
Where do you want to put that compared to these? Higher. Okay, we start here. There's some activation energy leading to this. We don't go straight there. It's an activation energy with a transition state. We get to this energy well. From here, this formation of the carbocation, then the nucleophilic addition. How much energy does this take? Is it going to be a lot of energy? No, it's pretty easy to fall downhill. So when you have two steps, you can say which is the rate determining step. Yeah, this is your biggest activation energy. This is your rate determining step. Ionization is your rate determining step. Nucleophilic addition, we can say this is fast step compared to the rate determining step. I think that's enough here. Let's propose another mechanism. By the way, this is going to be called SN1. We'll say why in a little bit. Questions? What's another way we could do this? Well, I think I'm just going to have to show you another way. We got to replace this, kick this off. We got to get this bonded here, get that kicked off. Another way we could do this is these electrons could just come in here and attack that carbon and kick that off. What was that? Backside attack. We've done that before when we attack bromonium and kick the Br off. What would this electron movement give? Here I had 2 arrows. What would that electron movement give? It would give that, wouldn't it? Because right here, lone pair is binding to carbon. Make that, and what is that arrow doing? Making Br minus, right there. Is that another way we could show the products? Yes, that's another way.
So that's concerted?
Yes, it's concerted. Good. Yeah. In, pushing it off. It's coming in, pushing it off. Okay. Why would these electrons want to come in here and bond to that carbon? Is there any rationale we could give why we want to do that? It is electronegative, thus this carbon has what? There is a partial plus there, partial minus there, there's a dipole. There's a partial plus, it's not a formal plus, it's not a carbocation like we made up there, but it is a partial plus. Which is going to be faster and easier, attacking a carbocation or attacking a partial plus? Attacking a carbocation would be faster. That's fast. Hydroxide adding there is going to be relatively fast. Attacking here, that's only a partial plus. It's not going to attack here as much. It's not going to be as eager to do it, but we could still propose it. If it happened, maybe it would require more heat or something to force it to attack there. Let's do a reaction coordinate diagram for this reaction. We start out with here. We end up with the alcohol. How many intermediates here? How many intermediates did we show? There's no intermediate, is there? Where's it at? No. We did have a transition state where this is bonding and that's breaking. There's a transition state. What does this look like? There's no intermediate, is there? There's no trick here. Do you see an intermediate structure? No. No intermediate. This is just an activation energy leading to that product. Just like that's an activation energy leading to that product. It's just this one, this intermediate was higher. I mean, if this was down here, you'd still have an activation energy leading to it. That's it. So which is the mechanism? Well, as we always avoid primary cations, we would say this one. Did we make a carbocation down here? No, we did not. So you might say, well, if we never do primary, it must be this. Well, let me give you some evidence, something else to consider. Kinetics. Kinetic studies have shown that the rate of the above reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. You change the concentration of this, it affects the rate. You change the concentration of that, it affects the rate. Either one, it affects the rate. Since the rate depends on both of the substrates, it depends on both. Because we know if you change the concentration of either, it affects the rate. How do you determine that? You do the reaction, you change the concentration, you do the reaction again and see if the rate changes. Change the concentration, see if the rate changes. That's been done. The rate changes if either one of these changes. The rate depends on both substrates. Thus, each must be involved in the rate determining step. This experimental evidence tells us that both are involved in the rate determining step. Look at your two mechanisms. In which mechanism is both substrates involved in the rate determining step? By the way, we didn't label the rate determining step over here. What's the rate determining step? There isn't one? Well, that's not the answer. How many steps over here? This was one step. One step. Which step was the rate determining step? That step. Right? So, which mechanism are both substrates involved in the rate determining step? Are both involved in the rate determining step over here? Is hydroxide involved with this ionizing? No. Hydroxide is not involved in the rate determining step here. Thus, you can change the concentration of hydroxide and it should not do any change. But the evidence tells us that changing hydroxide changes the rate. Is hydroxide involved in the rate determining step over here? This step is what? This is hydroxide doing this. I mean, this is the activation energy for this. Both are involved here in this step. Both are involved in a rate determining step. So we call this mechanism substitution by a nucleophile bimolecular. SN2. 2 meaning bimolecular. Two different molecules are involved in the rate determining step. What do you want to call this mechanism? It was a substitution by a nucleophile. How many substrates or reactants involved in the rate determining step? Only one. That's called an SN1. Which mechanism does the kinetic evidence support? SN2. SN2. The rate of an SN2 would look like this. Some type of rate constant, which is an inherent value for each reaction type, determined experimentally. But you then multiply that by the concentration of the things involved in the rate determining step. Both are involved. That's what this told you. Since both are involved, it's SN2. The mechanism is the one we showed here. It's a direct concerted displacement of the leaving group. There's no carbocation formed because we would not want to form a primary carbocation. That example reaction is an example of an SN2. What type of stereochemistry do we expect for an SN2? A concerted backside attack displacement. Look at this reaction. It's very similar to the first reaction, except we have an additional carbon added to make this chiral. This is R. If you react this substrate with hydroxide, on the front side we didn't show potassium, did we? We just showed hydroxide. Well, you can't just go to the stockroom and say, give me some hydroxide. You got to get the cation with it also. Right? You can't say, I don't want the cation. It's going to be there also. It's called a spectator ion. Potassium hydroxide, lithium hydroxide, sodium hydroxide. Hydroxide. Right? This looks like a substitution reaction. Br, the leaving group replaced by hydroxide. We make Br minus, spectator ion is there, we can show it as KBr. If you do this reaction, R, and this is now S. Only S. It's an antioselective. Is this SN1 or SN2? This is SN2. Why is it SN2?
That side of site means that one group before another speed.
Well, let's look at this. What is SN1? What's the first step of SN1? By the way, later on we may have a pre-step before this. Right now the first step is ionization, and we would make that carbocation, right? If this ionized, and this would be Br minus. There's the Br minus. If hydroxide then attacked carbocation, would you only get S? What would you get, Asian? Why would you get S or and R? Because how do you attack carbocations? Either side. If this was the mechanism and you ionize first, you should get S and R. But this reaction is known to only give S. Why? Because it doesn't involve a cation. The mechanism involves hydroxide coming in here, kicking this off in a concerted backside. We said it before, anytime you attack a carbon and kick something off, how do you attack it? Backside. The bromine is back, so backside is actually from the front. It's really called opposite side. The bromine is going to the hull, so we attack from our side, kick it off. Hydroxide is now forward, and this is called inversion. Inversion of stereochemistry. SN2 gives inversion. SN2. What does SN1 give? It would give both S and R. What do we want to call a reaction that gives both S and R? SN1 gives racemic because SN1 involves forming a carbocation. You attack carbocation from either side. So stereochemistry is an important consideration for predicting mechanism. Question though, is SN1 more or less likely for this reaction compared to the previous example reaction? If we did SN1 here, what does SN1 involve? First step? Ionization. What type of cation would we make if it ionized? Secondary. Is that more or less likely than the previous reaction? Previous reaction we showed a primary cation upon ionization. Now we're showing a secondary. This is more likely to be SN1. But how do we know it's still SN2? Because we got inversion. It must be SN2. Stereochemistry is used to predict mechanism. Which mechanism does the experimental evidence support? Well, SN2. The experimental evidence was the inversion. Mark.
Okay, so if the product was not given, how would you judge if it's SN1 or SN2? If you had like tertiary carbocation?
Good question. We'll get to that as we move forward. Yes. Good question. We're going to build to being able to answer such, because there's other things to consider. Right now, I'm kind of introducing the stereochemistry. Yeah, we'll have to be able to answer that. How is inversion obtained? A look at the SN2 transition state. I had this on here now. Ding. Let's see if we can illustrate the backside attack and I didn't bring mine. Let me see if I can reproduce the transition state here. This is for the example reaction. We're going to have a transition state that looks like this. I'm going to draw in that carbon, Br. The carbon with the Br has an ethyl, a methyl, and a what? Ethyl. I got to make sure I get the R and S right. I may have to redraw this. Let me draw it and look at it and see if I got it right. We got a methyl and an H. I may have to put the H on the bold. Let me see. That would come from carbon, bromine. This would be in the plane, the ethyl, the methyl, and the H. Is this R? H is in the back. We got bromine. Hey, this is R. 2, 3. Clockwise, H in the back. Yes, good. That's R. Okay. This is the compound at the top. This says R. I've just drawn it a little bit differently, but it's still R. It's a carbon with a bromine, a methyl, ethyl, and an H. The hydroxide, we're going to do SN2. The hydroxide, how does it come in and attack this carbon? Does it come in over here? Where? Opposite side of Br. We call it backside. The Br is projected that way, so the hydroxide is going to come in right 180 degrees opposite. I drew the Br in the plane so the hydroxide could come into the plane. Not forward or back, but I'm in the plane of the board. As it comes in, what does the transition state look like? Well, this is it here. We have hydroxide bonding to carbon. It's like making a partial bond. The bond is forming. That's what this means. Hydroxide is minus here. What's the charge of the hydroxide here? Let's draw the final product. Final product is going to have carbon with OH. It's going to have that and that. In the reaction, the hydroxide is minus, but at the end it's neutral. Plus what? Br minus. So what's the charge of the hydroxide as it's making the bond? When it's totally making, it's neutral. What's the charge here? It's halfway to making the bond. Partial minus here. It goes from full minus. As it's making the bond, the charge goes down to partial minus. As the bond is completely made and that's kicked off, the hydroxide becomes neutral. Br is neutral. Over there it's minus. What's the charge of the Br here? As this bond is breaking. Partial minus. This is the transition state. The energy of this is the energy that was at the top of that up here. This was the transition state energy that we drew before. It's the energy of that intermediate. It's not an intermediate, it's a transition state. When we say it's intermediate, intermediates can be observed. Transition states really can't be observed either. This shows hydroxide coming in backside. This is R. What happens here is tetrahedral, these groups are sort of like this with the Br coming. A model would have here too. These groups are like this. Hydroxide comes in. The Br is over here. Hydroxide comes in. What do these groups do when the hydroxide comes in? they sort of come flat and planar. They go like this. This here is supposed to be planar, where the methyl is actually right in front of the H. Okay, it's supposed to be like this. The carbon with the three groups planar actually looks like trigonal planar. Trigonal planar here. It's three things around carbon. What type of bond angles do we have for trigonal planar? Over here the bond angle is 109.5 because it's tetrahedral. This is trigonal planar like. What type of bond angles do we have here?
120.
Yes, 120. The transition state is trigonal planar like. sp2 like. If that carbon was sp2, it would have three hybrids. What would be left over? A what?
P orbital.
P orbital. And the p orbital would be perpendicular to the trigonal planar. Well, that's kind of what we got here. If we drew a p orbital here, that carbon is looking a lot like an sp2 carbon. Trigonal planar with a p orbital. And the two things that are kind of transitioning on and off are kind of like this. In the end, the transition state looks like sp2. Do you see how it looks like sp2? Trigonal planar with a p orbital. And so these things are like this. This comes in. These straightened up to become planar. But then as the leaving group gets ticked off, what do these groups now do? Now I can't bend my hand like this.
So that's
They actually come this way and go back to tetrahedral. Boom, planar, and then boom. The hydroxide pushes those groups that way, and now it becomes tetrahedral again. And now it's back to 109.5 tetrahedral. And this is called inversion. It's like an umbrella. An umbrella is like this over your head. Have you ever had the umbrella go the other way? But there's a transition state. For the umbrella to go the other way, it first has to go planar. You don't see it because it happens so quick. But then it goes the other way. Right? It's kind of what this is doing. It's called inversion, or Walden inversion. Walden is the person who really described this. This is important though. The bond angles become 120 degrees in the transition state. And you sometimes see questions like this. For example, what if you have a substrate and it cannot achieve 120 degree bond angle for some reason? Are you going to be able to do the transition state? You would not be able to do it. And thus the SN2 would not occur, or would occur very sluggishly. The 120 degree bond angle here, that's one application. Another application is, because there's a p orbital here, essentially, we can stabilize the transition state. How can we stabilize it? One way is, what if there's a p orbital next door? Or maybe more than that. If there's a p orbital next door, the p orbital that's formed in the transition state can start overlapping, and would that be a good thing? Yes, orbital overlap is good. So we have potential for p orbital overlap in the TS. You'd have to have a p orbital next door. Here's the take home. If you got a p orbital next door, it can overlap with that p orbital. It will stabilize the transition state. Drop this energy down. Don't draw this, I'm just going to do it quickly. If you drop this energy down compared to here, is that going to make the reaction faster? Yes. Okay?
So having a p orbital next door will lower the transition speed.
Yes. And this is what's talked about next. The effect of a p orbital being immediately adjacent to the reaction site. It will stabilize the transition state and make the reaction faster. What type of mechanism are we talking about? SN1 or SN2? We're talking about SN2 here. Backside attack conversion. This is the SN2 transition state. Let's end by showing this last bit here. We're going to start talking about the electrophile. The electrophile is the thing that contains the leaving group. The nucleophile is like the hydroxide. We're going to focus on the electrophile for a while. One thing we can say is, if there's a p orbital next door to the carbon that has the leaving group, it can be stabilized. If hydroxide attacks this, kicks it off, this carbon becomes sp2-like with a p orbital, but what's next door? P orbital. What's next door? P orbital. What's next door? P orbital. What's next door? Actually 2 p orbitals, but only one of them could be conjugated with the transition state. Here's the take home. All of these molecules right here are super reactive in an SN2 because they have a p orbital next door. All these molecules here are thus very toxic because your body has lots of nucleophiles, your DNA, proteins. And we can have like DNA with an amino group, and these electrons could come in here and kick that off. That's very easily done because the transition state is stabilized by this p orbital. That makes those compounds very reactive. Good for the lab, but bad for your body. Because if molecules react with your body, that's toxicity. Okay, we're out of time here. Please look ahead. We're going to look at variations on the group, the thing with the leaving group. That was one consideration. We're meeting downstairs this afternoon.